Today we are going to add normal mapping to our game engine. A normal map is an image that contains detailed surface information for a 3D model. When we have a 3D model, we can add a diffuse map to add an image texture to its surface. However, this still looks pretty flat, and if we want to add some little scratches and little bumps and scuff marks to the surface, then we can use a normal map. Let me show you this in Blender. This is the 3D model, and now I'm going to apply the diffuse map. It looks like a barrel now, but also here it looks pretty flat. So now I'm going to add also the normal map. And there we go. So now we have a surface structure here that makes it look more realistic, more like an actual barrel. In our game engine, it looks like this. This is how the diffuse map and the normal map for this 3D model look like. This is what we're going to do today. We need to calculate a tangent for each vertex on the CPU and add it to the vertex buffer. So normals we already have in the vertex buffer. Normals we get out of the mesh data right away. Then we need to load the diffuse and the normal map. Then we need to add a new component for normal maps to our entity component system. And then we will add a new render system that is just for normal maps, which is based on the diffuse and spectral lighting that we discussed before. To understand normal maps, we need to introduce a new term, tangent space. Tangent space is defined per vertex, and X and Y are in the plane that a triangle spans. The origin is where the vertex is, and then perpendicular to the triangle or perpendicular to the plane that the triangle lies in, that is where the normal vector 0, 0, 1 is defined. The range for each component of this vector x, y, z is from -1 to 1. If we want to put this in an image, though, we need to map it to a range from RGB 0 to 1. So we divide this range -1 to 1 by 2 and add per component 0.5. So our default normal vector that is just pointing up with 0, 0, 1 becomes RGB 0.5, 0.5, and 1, which is this bluish color that normal maps look like. In our shader programs, we will not only need the normal, we will also need a tangent. So which here is this X component in this picture. And to calculate the tangent on the CPU, we will make use of the UV coordinates. So to map the diffuse map and all the individual parts that are in there onto the 3D object, the 3D model has UV coordinates. UV coordinates are used to define a sub-area in an image. So this is shown here in the upper right corner. So this image here is a diffuse map. And here on the left lower corner, the UV coordinates is 0, 0, and on the upper right, it's 1 and 1. And so then sub-areas of this image are defined with UV coordinates. So if we wanted, for example, to draw a quad, we would draw it with 2 triangles. And that means we would require 4 vertices. And I put in here some example UV coordinates. So these in the vertex shader would be retrieved from the vertex buffer, and then per fragment in the fragment shader, it would be interpolated between vertices. The 3 vertices of a triangle can be anywhere in a 3-dimensional space, as shown in this picture down here. However, the UV coordinates are a 2D projection onto this triangle, and we can use it to calculate the tangent and bitangent. The picture here on the right shows a perpendicular coordinate system made out of a vector t, which is the tangent, and a vector b, which is a bitangent, and shows a triangle here with an arbitrary orientation. It has 2 edges, E1 and E2. Now, the delta of the UV coordinates can be found in this picture. So E1 is composed of the vector delta t times delta U1 plus the vector b times delta V1, which is this distance here. And for E2, it's the same. It's composed out of vector t times delta U2 plus vector b times delta V2. This equation can be written in matrix form, so which is shown here. On the left side, we have E1 split up into its components x, y, and z, and E2 also split up in x, y, and z. And then on the right side here, we have matrix multiplication. And one of the matrices here is already a matrix composed of T and B. So this is what we're after. Now we need to divide this equation by this matrix with delta U and delta V, so that the matrix composed of T and B is isolated. The result you can see down here. We have T and B on the left side isolated, and we have the inverse matrix here already calculated. So on the right side here, everything is known, and the unknown, the tangent and bitangent vectors, are on the left side. And this is what we can calculate in the CPU. In the C++ code, where we load the model from the obj wavefront file, which is shown here, we add another loop down here after the loop where we extract all the indices and all the data for the vertices. And here we loop again over all indices, and we maintain a counter that counts from 0 to 2 and then wraps around. The counter is created down here. So that if the counter is 0, we are at vertex 0 per triangle. And just remember the position 1 and UV1. Then if the counter is 1, we are at vertex 2 and we remember position 2 and UV2. And if the counter is 2, we get position 3 and the UV coordinate 3. And then we perform the calculation that I discussed and showed before. So we calculate E1 and E2. These are three-dimensional vectors. We calculate the delta U, and we calculate the delta V. So then we map this onto the same names that we had in the equations. We calculate this factor here, which was shown down here. And then we go ahead and calculate the tangent, each of its three components, x, y, and z. And then we store the tangent in the vertex buffers for all three vertices. So we are done with our first to-do. Now we need to load the diffuse and the normal map. In the constructor of VK renderer, where we create the descriptor sets, we add to the descriptor pool two combined image samplers. Then for the global descriptor set layout, we add two combined image samplers as well. Then we need to load the actual data. Here. So from the texture slot manager, we get a texture slot and create a shared pointer for the texture, for the diffuse map of the barrel. And we initialize it with barrel PNG. That's the diffuse map image on the hard drive. Then we need to add the descriptor image info, and we add the sampler, the texture view, and the image layout. Then we need to do the same for the barrel normal. So for the normal map, this is this code. So it's identical. It's just yet another image that we load. And then in our descriptor writer, we need to add those image info structures and then build this into the global descriptor set. Load, diffuse, and normal map also done. Next, we will add a new normal map component to our ECS. So that's our entity component system. In model.h, by the way, we have the vertex structure, which now has a tangent here, a vec3 for the tangent, and then in scene.h, we have our components. So far we have, let's see, a transform component, a mesh component, a point length component, a rigid body component, and then we have a diffuse map component. So this is for models without a normal map. And then we have a structure, a normal mapping component that at the moment contains a texture slot, and then for the normal map texture, a slot as well. To add a new render system, we duplicate some code. So in Engine, Platform, Vulkan, and Systems, I copied the existing render system over and renamed it to VK render system normal mapping. Then I renamed everything from VK render system to VK render system normal mapping. Here for the shader pairs, I changed the file names to normal mapping, vertex, and normal mapping fragment SPV. And then in the render entities function, we now render over everything that has a normal mapping component. So from the ECS, we get a view onto everything that has a mesh, transform, and a normal mapping component. Then we push the constants accordingly and bind and draw the models accordingly. Also in the renderer, we must call it. So back in the file where we were before, VK renderer, we need to create the render system normal mapping here. Same as usual from we get the render path from the swap chain, and then we create it with the descriptor set layouts that we just discussed. And then in our submit function, we also need for each frame to submit the registry. So to call the render entities function in our new renderer system. Here's the render entities function, which takes in the registry. That's our ECS. So that's it on the CPU side. Now, all that's left to do is to take care of the shader programs. So for that, we copy also the shaders over. So I used our usual lit shader. That's that's the normal shader with diffused and specular lighting. So I copied that over and called it normal mapping. So these are here. What's new is the tangent in here. So in the vertex shader, we transform the camera and the light into tangent space. This has the advantage that we could do it the other way around. We could, in the fragment shader, for each fragment, transform the tangent space normal into world space, but that would then run for each fragment. And since the vertex shader runs not that often, it makes more sense to calculate or to transform the camera and the light into tangent space and calculate the lighting then in tangent space. So to perform this transformation, we have to create a TBN matrix. So that's the tangent bitangent normal matrix. And then each light position is multiplied with the TBN matrix, and which is what we send down to the fragment shader, and then we do the same for the camera and also for the fragment world position. To get a hold of T, B, and N, we take the inverse transpose of the model matrix and then multiply that with the tangent and normalized, that is our T, then multiplied with the normal and normalized, that is our N, and then from T and N we just need to do a cross product, which gives us the bitangent. There is one step in between here, which is called Gram-Schmidt. This is done if two vectors are not exactly perpendicular anymore, which may occur already in the model or due to some smooth shading, then this can be readjusted so that they are orthogonal again. So yeah, then if we build the cross product, we have also the bitangent, and then we build a mat3 matrix. A 3x3 matrix is used in this case because we are dealing with directions and not with positions. So normally when we are using 4x4 matrices, like up here for the model matrix, then we are dealing with positions, and positions can also be translated, while directions can't. So directions are, wherever they are in space, they are always directions. They can be rotated and scaled, but directions can't be translated. And that's why a 3x3 matrix works just fine. So in the fragment shader, we now also have a texture slot for the normal map. We have the camera position in tangent space, the fragment position in tangent space, and the light positions in tangent space. We have a sampler for the diffuse map. We have a sampler for the normal map. Then all the calculations we do for the lighting are still the same, only that the inputs are now from tangent space. So here, for example, the to camera direction. And most notably, now we get the surface normals from the texture. So what we do is we said the data in the image is scaled from 0 to 1, but we need it to be scaled from -1 to 1. So we multiply each value by 2 and subtract 1. And then we need to re-normalize it. So yeah, the rest is just the same. Yeah. This concludes the video. Then we're also done here. That's our new render system with the new shader pair. And that's normal mapping. Thanks for watching.